Hello everyone. So this is the third lecture of carbon compounds, and in the last class we had discussed about the allotropes of carbon, and before that we had understand how the origin of organic compounds has happened, or how did we discover that what are organic compounds, and how did we get to know that, how did we got to know that how to synthesize organic compounds. So basics of what exactly organic chemistry is and what our hydrocarbons are, why carbon is important, why it is an essential element, and then what are the sources from where we can get the organic compounds, and then how carbon exists in nature, what are different allotropes of carbon. We have all discussed that in the last few videos. Now, in this video, we will be majorly talking about how to classify organic compounds. Now, we have got the basic information about organic compounds. Now, we have to understand that there are millions and millions and trillions of organic compounds on the earth, and definitely we cannot know about each and every organic compound just by naming them, or even if it's just talking about the names, not even their properties. We cannot remember so many names, we cannot remember so many properties and all these things. So it is easier to classify organic compounds, put them in certain category where one category of compounds will behave in the similar fashion. For example, if I talk about, let's say, in a class, there are three kind of divisions. We talk about one is above average students, then average, and then below average. So basically, in a class of 50, if there are three divisions I'm making, the 50 students will be divided in three categories. One is above average, one is average, and third is below average. So when we say above average, some of the characteristics will be same in the case of those all the students who belong to that above average. Similar way, when we talk about the average students, all the average students will have similar properties, or you can say similar behavior, similar kind of responses to the questions given by the teacher, or similar kind of expectations we set from them. And in the similar manner, we will have it for below average students. So this is a very generic categorization which I have told you. It has nothing to do with the carbon compounds classification, but this is just an example because you have seen it throughout of your education life, and it will be easier for you to understand through this example. Similar way, we classify organic compounds so that it becomes easier for us to study the compounds and their properties. Now, as I mentioned, there are millions and trillions of compounds, so categories are also going to be a lot. We are not going to deal with all the categories right now, but the few basic ones. So in the grade 10th, we will be handling two basic categories, saturated and unsaturated compounds, and further divisions or subcategories of these two compounds, or these two type of compounds. Here again, I'm mentioning that this is not all about organic. This is probably a 0.1% or 0.1% or 1% of the organic what is there throughout. So it's a very small chunk, but still is a good considerable amount for grade 10th. So we will be talking about only very few compounds, very few categories. We will be learning how to classify organic compounds, how to identify a particular organic compound belongs to which category, and then talking about how to name them and then their properties. So this will be the course of next few videos, you can say. Today, now we are going to talk about classification of organic compounds. So when we are talking about classification of organic compounds, which in general I can also say hydrocarbons, you call it hydrocarbons or you call it organic compounds, one and the same thing. Okay, hydrocarbons is a more precise word for grade 10 because we'll be majorly dealing with the compounds which are made up of carbon and hydrogen, and very few we'll be dealing with where we have some other elements also present like oxygen, chlorine, bromine, nitrogen, and so on. Organic compounds, when we say, it has all complex and easier structures. So organic compounds become a much broader category. Hydrocarbons have become one specific part which is majorly made up of carbon and hydrogen and have lesser number of oxygen, nitrogen, fluorine, chlorine, and all these kind of elements present. Okay, so here when we are talking about hydrocarbons classification, we have two type of hydrocarbons which we'll be dealing with. One is saturated and another is unsaturated. So here we have to understand how did we classify our hydrocarbons in these broader two categories. What was the basis of this classification? So basis of the classification of compounds under these two categories was the type of bonding exists between carbon and carbon. So if you remember, I told you carbon can tend to show carbon single bond carbon kind of bonding, carbon double bond carbon kind of bonding, and carbon triple bond carbon. So carbon is capable of making single bond, double bond, and triple bond with the carbon throughout. So basically it has that versatile nature where it can show you the single bonding structures also, double bonded structures also, triple bonded structures also. You can find in a compound a combination of double bond and single bond, triple bond and single bond, triple bond and double bond, and throughout the single bond. So there can be various combinations in a compound. So majorly how carbons are linked to each other in the compound, that is the basis of the initial or the most basic classification, and most basic classification is division in saturated and unsaturated hydrocarbons. Now what are saturated hydrocarbons? Let's talk about it. So saturated hydrocarbons are the ones in which when you talk about a carbon chain, when you talk about the organic compounds are linked, or you can say the carbon within the organic compound is linked throughout only with the single bond. So you won't find any double bond, any triple bond in the whole structure. I'm talking about the carbon-carbon single bond. I'm not talking about any other group present here. I'm just talking about if you have a compound and in that compound you have throughout only carbon-carbon single bonds, then the compound will be called as saturated hydrocarbon. Let me just show you it over here. So if I take the structure like the C, I have carbon. Each carbon has the tetravalency. So I can link the carbons like this, where carbon is linked to another carbon through the single bond, and rest of the valencies I have not shown filled yet, but I had mentioned it in the last class also, and in the previous class before that also, that when we link the carbons to each other, the remaining valencies are filled with hydrogen. So now on these remaining valencies, which seems to be unfulfilled, will be filled by hydrogen. So I have made a chain of how many carbons? 1, 2, 3, 4, 5, 6. 6 carbon chain I have made, where all the 6 carbons are linked through the single bond, and the remaining valencies which were not fulfilled are eventually getting filled by the hydrogen, or these positions have been filled by the hydrogen. So I have filled it with the hydrogen. Just look at it over here on the screen. So this is my compound. This is a compound which I am talking about, and in this compound what can we see? We can see that the carbons and carbons are linked with each other with the help of only single bond. Any such kind of compound will be in the category of saturated hydrocarbons. So saturated hydrocarbons are the ones where you will find the carbons linked with each other through the single bond. We have another name for saturated hydrocarbons, and we also call them alkanes. So there are two names for such compounds, saturated hydrocarbons and alkanes. You can call them anything. Saturated hydrocarbons is a very generic, you can say generic term, and alkane is a very specific term to the types of compounds. So hydrocarbon, so let's see the definition over here. Hydrocarbon in which the carbon atoms are connected through the single bond are called as saturated hydrocarbons, and are also called as alkanes. Now let's see the table over here, or the diagram which I have drawn over here, or you can say the classification which has been shown over here. That is, hydrocarbons contain only carbon and hydrogen. As I mentioned earlier, that when you talk about organic compounds will have carbon, hydrogen, and some other elements also like oxygen, nitrogen, fluorine, bromine, iodine, and so on. But when we are talking about hydrocarbons, it is specifically dealing with the compounds which are made up of carbon and hydrogen and do not have any other element present in it. And that is why I have mentioned this classification is for hydrocarbons, not for organic. When you talk about the organic chemistry in general or organic compounds, the classification becomes much more wider, and there are a lot many other categories, not only saturated, unsaturated, or alkane, alkene, or alkynes. Okay, so here hydrocarbons, as I mentioned, has been divided into saturated hydrocarbons and unsaturated. I told you this saturated and unsaturated division has been made on the basis of how the bonding is between carbon and carbon. So saturated is the one where there are no carbon multiple bonds. That means there is no double bond, no triple bond. It's only single bond which exists within the chain, and we call them alkanes also. Next comes to the category that is unsaturated hydrocarbons. When we are talking about the unsaturated hydrocarbons, unsaturated are the ones where you will find multiple bonds also along with the single bond throughout the chain. For example, if I take a chain like this, just see it on the board over here. So if I have taken the chain like this, where carbon is linking with another carbon with a single bond, and then suddenly it starts forming a double bond. Let's say this is the compound, okay, where 1, 2, 3, 4 carbons were linked with each other with the help of single bond, and then one pair of carbon are attached to each other using double bond. Now the linking is over. I wanted a chain of 1, 2, 3, 4, 5 carbons, and then remaining valencies will get fulfilled by hydrogen. So I have written hydrogen over here. And here is my compound with the fulfilled valencies, and this is the compound which I am going to refer while explaining you unsaturated hydrocarbons. So here in this compound, what you can notice is this compound has two kind of bonding structures. One is carbon single bond carbons in the chain, as well as carbon double bond carbon. So basically the chain does not only consist of carbon single bond carbon, but also has carbon double bond carbon. So that means here is the existence of single bond as well as double bond both. So in this chain, you will find, or you can see, that you have two different kind of bondings present: single type of bonding and multiple type of bonding, and such kind of compounds comes under the category of unsaturated hydrocarbons. Now let me make a small change in the same compound. So let's say if I draw one more bond over here, and here is the new compound. I have changed the valencies over here. I mean, the valency is same. I have changed the structure a bit. This first carbon has formed a single bond with another carbon. Second carbon is also bonded with the third carbon using the single bond. Fourth carbon and fifth carbon are linked to each other using a triple bond. Now, the fifth carbon has one bond, single bond with hydrogen, whereas a triple bond with the fourth carbon. In this compound, what we can see is we have two kind of bonding combinations over here. One is carbon single bond carbon, and another is carbon triple bond carbon. So in my chain, again, two different type of bondings exist. One is single bond and another is triple bond. Majorly the whole chain is bonded with a single bond, but at a certain place in a pair of carbon, you can find double bond or triple bond, and such kind of compound will also comes under the category of unsaturated hydrocarbons. So that means, what are unsaturated hydrocarbons? The hydrocarbons which consist of multiple bonds. That means the single bond is a natural behavior, or you can say is normally what we find in the organic compounds, or normally we find in the hydrocarbons. But if there is a presence of a double bond or triple bond also, then we call it under the category of unsaturated hydrocarbons. That means it has two different type of bondings which are present. One is carbon single bond carbon, and another is carbon multiple bond carbon. But multiple bond can be a double bond also, and can be a triple bond also. And this broader category will be called as unsaturated hydrocarbon. Now, if I have to refer to a specific compound where you have a combination of carbon single bond carbon, you have a combination of carbon single bond carbon and carbon double bond carbon in a chain, and I have the another combination as carbon single bond carbon and carbon triple bond carbon in the chain. So how will it be different from each other? Because both of them comes under the broader category, that is unsaturated hydrocarbon. So how will we figure out whether we are talking about the combination of carbon single bond carbon and carbon double bond carbon, or carbon single bond carbon and carbon triple bond carbon? How will we distinguish it? So basically, this also has been further subcategorized and has been named in a little different manner. So the combination of carbon single bond carbon and carbon double bond carbon compounds is called as alkenes. This has been given a specific name, that is alkenes, whereas the combination of single bond and triple bond combination is called as alkynes. So we have basically categorized the hydrocarbons in two basic categories. One is saturated, another is unsaturated. Saturated tell us that there are only single bonds. Unsaturated tell us that there are single bonds as well as multiple bonds present in the compounds. Now the unsaturated is further divided into alkenes and alkynes depending upon whether you have a double bond presence in the compound or a triple bond presence in the compound. And there comes a third category also, which is called as aromatic compounds. So I'll tell you what are aromatic compounds, but right now the most important is division of saturated and unsaturated hydrocarbons in alkanes, alkenes, and alkynes. So look at the table again over here. So we have unsaturated hydrocarbons, the compounds which contains carbon-carbon multiple bonds, and we can further subcategorize it into alkenes, alkynes, and aromatics. Aromatics are nothing else but aromatic compounds. Aromatic compounds. And I'll tell you what are aromatic compounds now. I'll not give you very detailed explanation of aromatic compounds because it is way beyond your scope of understanding. You will be learning it in grade 11th in much more detail, and it is going to be a very important topic as well as very important part of organic chemistry. You can say half of your chemistry relies on this aromatic compounds, but for now it is not there in grade 10 syllabus, and you just need to know very basic terminology, very basic understanding of aromatic compounds. So let's talk about the aromatic compounds also. Aromatic compounds, again, as I mentioned, this may not be a very precise definition of aromatic compounds because that is something which you'll be learning in grade 11th and requires a lot more in-depth knowledge of organic to understand what is aromatic compounds, what are aromatic compounds. Here I'll be telling you a very generic information about aromatic compounds which you can use for now. Aromatic compounds are the ones which are benzene based compounds. Now you will ask me a question, what is benzene? We have never heard of it. So benzene is a type of a compound which has structure like this. Look at it over here. CH2, 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 CH2. Or let me just draw it in a different manner so that you get more clarity. So basically, 6 carbons have been linked with each other in a cyclic structure, the closed chain, where we have alternate double bond and single bonds. So alternate double bond and single bonds present over here. And then let's talk about the fulfilling their valencies. So here we have 3, each carbon has already made 3 bonds, so one valency would be unfulfilled in each case. And let me fill up that valency with hydrogen. As I mentioned, the valencies will be filled by hydrogen always. This structure is called benzene. Okay, so here what has happened, 6 carbons have not linked with each other in a straight chain, but a cyclic structure, the closed chain structure where you have alternate single bond, double bond, single bond, double bond, single bond, double bond. Now why we have considered this into the unsaturated hydrocarbons, because as I mentioned, unsaturated ones are the ones where we have the combination of single bond and multiple bonds, and here we have multiple bond as a double bond. Correct? You can have one double bond, you can have multiple double bonds also. The most basic form of unsaturated hydrocarbon is the one in which at least one pair of carbon must have double bond or triple bond. Okay, so this benzene structure can also be written in more simplified manner like this way. So we make an hexagon and then we just draw the bonds alternatively. Here I have not written carbon or hydrogen. This is one type of representation of the chain. We will be talking about this in our videos. This is called as bond line representation. Bond line representation. So this basically helps you in drawing organic compounds in a more simpler way, where less clumsier the structure would be, because you won't show carbon and hydrogen. You will understand just through the lines. So you will just draw the lines and it will tell you what compound it is. Bondings will remain as it is. So you can see in this structure neither the carbon has been mentioned nor hydrogen. It's just the hexagonal structure has been made and the double bond, single bond alternatively. This further can be drawn as this. a circle in the center. Why there is a circle in the center? That you will be learning in grade 11. This circle in the center means these double bonds are not fixed to a place. These will rotate. Basically, they will change their position. So if you talk about benzene, benzene can have this kind of structure also. So look at this. Is this structure any different from, let's say this is structure 1 and this is structure 2? Are these two structures different from each other in any way? No. But if you refer to this structure, then you will see, and if I mark the carbons, let's say this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. Similarly, carbon 1, 2, 3, 4, 5, and 6. What you will see that earlier in the first diagram, there was a double bond between first and second carbon, whereas here in the second diagram, you can see the double bond between first and sixth carbon. So basically, double bonds position have been changed. But structure, if you look at, because the structure is symmetric, we can't find any difference between structure 1 and structure 2. So what we say is that the double bond keeps changing its position, but it will be in such a way that it will be always alternate to the another double bond. It will never be together. So two double bonds will never come together. If one double bond will shift its position, the other double bond will also shift its position. And that is the reason why we put a circle in between, which represents that the double bonds are changing their position throughout. Why it is happening, how it is happening, we'll be learning in the next grade altogether. It is not required right now. It is just to tell you that what is benzene. And any compounds which are made up of benzene and benzene itself is called as aromatic compounds. Okay, so this is the third category of unsaturated compounds, that is aromatic compounds. Benzene based compounds or benzene will be considered as aromatic compounds. There are other few compounds also which are not benzene based but still considered as aromatic, but we will not talk about it at all. It will just lead to the confusion and you don't know the basics of aromatics, why we call it aromatic, what kind of specific behavior these compounds exhibit. All this we'll be learning in the higher grade, and hence we'll talk about aromatic compounds in much more detail in grade 11th. So I have given you the basic definition of what are alkanes, what are alkenes, and what are alkynes. Let's talk about alkanes in a little more detail now. Alkane is a hydrocarbon in which carbon atoms are connected only through the single covalent bonds. Already told you, carbon makes the covalent bonds, doesn't form the ionic bonds. Hence, these single bonds are going to be covalent bonds only. Now, when we are talking about the compounds formed in alkane, the carbons which are linked with each other through the single covalent bond, what kind of different shapes they take, and which one is the smallest alkane. So here I have shown you the two diagrams. One is this one and one is this one. Just try to understand what I'm trying to explain you over here. So if I talk about the alkane formed by the single carbon, then single carbon has a tetravalency. It will not link with any other carbon, but all the four bonds it will be filling, or the valencies it will be filling using what? Using hydrogen. So I can write it as carbon with hydrogen, 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 and hydrogen. This is how I will represent my smallest alkane. This compound has four bonds filled with the hydrogen, no bond linked to the carbon. So basically all the single bonds have been formed with the only hydrogen, no carbon. Only single carbon in the center. When you look at its shape and structure or geometrical figure, how actually it exists, what kind of bonding or how the hydrogen atoms have been arranged around the carbon atom, it will be this way. Look at the diagram here. So here carbon is in the center. Here the carbon is in the center. This is my carbon. And if I talk about hydrogens have been arranged like this. Here, 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 and here. So let me just show you how it actually looks like. So it is like this. One bond here, then here, and then here. So guys, this which I'm trying to explain you through the diagram over here, which I said this is the 2D representation of a 3D structure. Let me just show you the actual 3D structure of the smallest alkane, and this is how it looks like. So as I mentioned, all of you look at me, not on the written part of your slide. So this is your alkane, the first smallest alkane, where this carbon, which you can see over here, this is a black color thing. Black color ball is the carbon, and these white balls represent hydrogen. Okay, so these all bonds. Look at it, how it looks like. All these bonds are equidistant to each other. If you draw a 2D representation of it, it looks like that these two bonds are closer and these are far away. That's how it looks in the picture also, but that's how exactly it is. This is your smallest alkane. And the angle between this carbon hydrogen and this carbon hydrogen bond is same. So this is the angle. I hope all of you understand what does the angle means. So this angle is same as this angle and same as this angle and same as this angle. So these angles are going to remain same, as well as the distance of carbon and hydrogen, or you can say this is the bond, this white color thing is the bond, and this bond length is also going to remain same in the case of all the four hydrogens. So this bond distance, that means distance between carbon and hydrogen, is called as bond length. Whereas the angle between one carbon hydrogen and another carbon hydrogen bond is called as bond angle. Bond angle as well as bond length is going to remain same throughout. That means the bond angle between one carbon hydrogen and another carbon hydrogen's, not one carbon hydrogen, basically carbon hydrogen this and the another carbon hydrogen bond is still going to remain same, no matter you're talking about this combination or you're talking about this combination or you're talking about this combination or you're talking about this combination. And the length of or the distance of carbon and hydrogen is also going to remain same, and that is called as bond length. Okay, so this is what I'm going to show you over here in the diagram. So this, if you can see, this looks like a tetrahedral structure. If you draw the lines here to see what the shape is, the shape is tetrahedral. It is a tetrahedral shape. So this, look at the diagram over here now. This is the tetrahedral shape, and we have just linked the lines are actually, lines do not actually exist. This is how the molecule would be. We have just drawn the lines to understand what shape it forms. So this is your tetrahedral molecule. This is how actually a molecule looks like. This dash shows, if I show you my molecule like this, let's say if I'm showing you molecule like this is my molecule. There are few things which you can say, which you can see in the front, and this bond is at the back, and the back bond is generally shown by a dash, though you don't have to get bothered about it much because you won't be asked about it. This solid, this kind of solid which has been drawn, and this kind of dash which has been drawn, has a specific meaning. This wedge means this is the direction from where the viewer is seeing. So this, let's say you are seeing from here, this is the bond which you are able to see towards you. Okay, the outwards, coming outwards, and this is represented by this solid triangle sort of thing, which is also called as wedge representation. The bond which is towards the viewer is represented by the wedge kind of structure, and the bond which is away from the viewer, that is facing towards me, okay, that is represented by a dash. So you really don't have to get bothered about it because it is not something which they are going to ask you. It is going to be there in grade 11th, and you are going to learn it in much more detail. It is just to show you that how do we show the organic compounds, how the smallest organic compound or smallest alkane looks like in the actual form also, and what is the bond angle, how it is shaped, and all this. This is just to represent the shape of the molecule, that's all. Okay, so here you can see the bond angle between each carbon hydrogen bond is 109 degree, and that is throughout. This is between this bond, this bond, and this bond also. This same angle will be here also 109.5 degree. This will be same here also 109.5 degree, and this will be same here also 109.5 degree, no matter how my molecule looks like. It looks like these two are closer, these two are a little far, and these are the farthest, but that's not how it is. I've shown you how it looks like. Okay, this is just a 2D representation, and 2D representations can be deceiving sometimes. Similarly, I can draw the another next bigger alkane, or you can say next alkane after the single carbon alkane. What will be the next alkane? Where you will have two carbon atoms linked to each other through the single bond, and I can draw it this way. Carbon and carbon is linked to each other through a single bond, and the remaining valencies are free, which will be filled by hydrogen. So I have filled it over here. Okay, This is my molecule where I can see carbon-carbon single bond and carbon-hydrogen single bonds. This is the next alkane in the list. Smallest was the one which was made up of only one carbon. The next is the one which is made up of two carbons. And similar way, you can make the longer and longer and longer chains of 3 carbon, 4 carbon, 5 carbon, 6 carbon, 7 carbon, 8 carbon, 9 carbon, and 10 carbon, and so on. We have till 10 carbons in our syllabus, and you should know all of them, their structures, their names, how they are represented, what is their molecular formula, everything you need to know. The first one which I had spoken about was the one with one carbon and 4 hydrogen, hence the molecular formula of it is CH4. Whereas the one which I'm talking about is made up of 2 carbons with the rest of the valencies filled with the hydrogen, and it has the formula C2H6. If I have to represent it in the 3D representation, how it actually looks like, this is how it looks like. All of you look at it very carefully. Look at me, not on the slide. Look at me. These are two carbon balls. If you can see, these black balls are the carbon balls. They are linked through each other with a bond in between. Bond has been represented by a white color rod, you can say, or white color tube sort of thing. And then these white color balls are the hydrogens which are attached on each carbon to fulfill the valency. And these bonds have been shown by a purple color link because the bond length is going to be different. The distance between carbon hydrogen and distance between carbon carbon is going to be different, and that is why it has been represented by a different color. When you talk about the angle, bond angle, bond angle will be between this carbon hydrogen and this carbon hydrogen bond, and this is going to be some angle over here which is going to be same as the angle between this and this, angle between this and this, angle between this and this within one carbon. Within one carbon, the angle between this set and this set, this set and this set, this set and this set is going to remain same, and that is approximately again 109 degrees 5 minutes. 109, let me just write it down. So bond angle between these is 109.5 degrees, or 109 degree 5 minutes, you can call it anything, or 109.5 degrees, you can call it 109.5 degrees. That's how we represent it. Okay. And as I mentioned, this bond angle is specific to one carbon atom. Similarly, the bond angles will be there between carbon hydrogen bonds in the another carbon, and those are also going to remain same, that is 109 degree approximately. And this is not only about CH4 and C2H6. No matter whichever alkane you take, carbon hydrogen bond angle is always going to remain same, that is 109 degree. That is why I mentioned in the beginning that when you categorize the compounds, there are some properties will match with each other and you won't have to remember it. So no matter I talk about the alkane made up of one carbon, alkane made up of two carbons, alkane made up of three carbons, four carbons, 5 carbon, 10 carbon, 20 carbon, 30 carbon, 50 carbon. When you talk about the bond angle between carbon hydrogen and another carbon hydrogen bond, that will always remain fixed, and that will be 109.5 degrees always. Always. Okay, that is the characteristic of an alkane, and that is how the bonding is similar in case of all the compounds of alkane. Now the distance between carbon and carbon over here, the distance between carbon and carbon over here, which has been shown by this white color rod, which is, I told you, is also the bond between carbon and carbon. Whatever the length of this bond is will be called as bond length between carbon and carbon, and then bond length is approximately 154 picometers. Obviously, you don't have to remember it. It is just for your reference to understand how the actual molecule looks like. All these values you don't have to remember right now, but more you know about them, more it will be easier for you to understand things, and things will look more realistic to you rather than mugging up all the concepts everywhere from here and there. Okay, so bond angle is between the one carbon hydrogen bond and another carbon hydrogen bond, that is called as bond angle, and that is going to remain fixed, that is 109.5 degrees always. Bond length between carbon and carbon is going to remain fixed, that is 154 picometers always, no matter whichever alkene you take. Okay, so this is the representation of C2H6. This was the representation of CH4, and these are two most basic alkanes what we have in the list. As you go higher in the list, the number of carbons will increase, number of hydrogens will increase, and hence the chain will become longer and longer. How can we represent these alkanes in on paper or in the 2D form? This is how we can represent it. I have already shown it over here once. Again, I can show you over here. This is carbon with 4 valencies. This is the smallest alkane I have, and we have a specific name to it, and we call it methane. Similarly, we have the chain of 2 carbons where 2 carbons have been linked with each other through the single bond. Remaining valencies have been filled by hydrogen, and it will be called as ethane. Similarly, I have 3 carbons here linked with each other. All the other valencies have been fulfilled by hydrogen, and this will be called as propane, and many more. How we have named them this? How would you know how to name them? Do you have to mug these names, or you can understand these names and give them the name on your own? All this we'll be learning in the next part. Next part as in next slide. You will understand in the next part where I'll explain you the nomenclature or naming of the organic compounds, how to name the compounds. But before I explain you naming of the compound, the most important part is to understand how these compounds can be written in different various ways. So we will understand how to write the compounds, or what is the representation of compounds on paper when it comes to write the formulas of these compounds, no matter it is alkanes, alkenes, or alkynes. So now we have got a broader understanding of alkane, how alkanes look like, how the two basic or smallest alkanes look like, what kind of bonding exists in alkanes. Now we'll talk about if I have to represent any alkane with the formula, how to calculate it. Do I have to write all the carbons, all the hydrogens, then count them and then write the formula? No, we have a shortcut to it, and that is called the general formula of writing alkanes. So general formula of writing alkanes or unsaturated hydrocarbons is CnH2n. So what do we mean by CnH2n? What exactly it means? CnH2n, n is a generic number. This n means starting from 1. It doesn't start from 0. It's a whole number starting from 1, goes till infinite numbers. Okay, and you just have to fill this n with a specific number and it will give you the formula. That means if I want to make an alkane made up of only 1 carbon, I will write n as 1, and the formula will become C1H2 into 1 plus 2, and this will become CH4. And if you remember in the last slide, this is what we have seen, that the carbon has 4 valencies. It is not linked with any other carbon, and the 4 valencies have been fulfilled by hydrogen. So that means the formula becomes CH4. So no matter you write it like this or you directly calculate it using the formula, the answer is going to remain same. Similarly, I have shown you the example of the compound made by 2 carbons where the carbon-carbon single bond is there and the remaining valencies have been fulfilled by hydrogen. So I could write it like this. My hydrogen is a little poorly written. I hope you will understand. So this is hydrogen. If I'll write it in short form, it will be CH. If I'll count total number of carbons, it's 2. Total number of hydrogens, 6. So this is the formula which I'm getting through drawing it and understanding the linking or the bonding. And if I fill this n is equal to 2 in this formula, let's see what do we get. We will get H2 into 2 into 2 plus 2. So it will become C2H6, the same result. For the smaller compounds, it is easier to draw the structure, understand how the structure is, and then calculate the formula. But when the chain grows, that means when the chain is going to be 20 carbon chain or 50 carbon chain, you cannot draw the 50 carbons, fill the valencies, and then count the number of hydrogens. Then it is easier to use the general formula and write the molecular formula of the specific alkane, depending upon how many number of carbons you want in the alkane. So you will get the alkane formula instantly. Okay, so this is about what is the general formula of alkane, where n means the number of carbon atoms. N is the whole number which starts from 1, goes till infinity. But obviously we do not calculate until infinity. You will get the questions majorly where n will have 20 as a number, 30 as a number, 15, 18, 17, the smaller numbers, not the bigger ones. So it's just a simple calculation, simple maths, and it can give you the right molecular formula of the alkane. Let's talk more about the alkanes. A last point for alkanes for now, and then we will talk about how to represent the formulas when it comes to talk about any particular compound, no matter it is alkane, alkene, or alkyne, how to represent it on paper so that we can have a better understanding of look and feel of the compound, and then we can talk about it in much more detail. So if I say that I have a saturated hydrocarbon, these are called as alkanes. These alkanes have one generic property, and that is these are less reactive. These are not very reactive molecules. These are less reactive in general because the carbon-carbon single bonds are very, very strong. So basically, when we talk about single bonds in general are quite strong, whereas when you talk about the double bonds and triple bonds, these are weaker bonds. Single bonds also have a specific name, which will definitely won't be mentioned in your NCRTs or in 10th grade syllabus, but it is good to know. Single bonds are called as sigma bonds. Sigma bonds. And the representation of sigma bond is like this. Okay. This is how single bonds or sigma bonds are represented, and sigma bonds are quite strong bonds. Whereas when I talk about the multiple bonds, that means if I'm talking about, let's say, carbon double bond carbon, in this case what will happen, there will be two bonds. One bond is going to be sigma bond, that is this, and another bond is going to be a weaker bond. Always, no matter what, always it is going to be a weaker bond, and that will be called as pi bond. Pi bond. Pi bond, and we represent it like this. So this is a weaker bond and this is a stronger bond. Now this is not only in carbon double bond carbon, but the same thing exists in carbon triple bond carbon also. Out of three bonds, one bond is going to be sigma bond and remaining two bonds are going to be the weak bonds. Those are pi bonds. So one bond is sigma bond and other two bonds, I think I should have made it with a different color. Okay, let me just draw it once more. So this is your sigma bond, and let me draw it with a different color now. This is pink color. Pink color bonds are your pi bonds. So this is your sigma, and these two are the pi bonds, or you can call them weaker bonds. So whenever the reaction takes place, existing bonds break and new bonds form. So when you talk about alkanes, alkanes have pretty stronger bond in them, and that is the only sigma bond. They don't have any pi bond, and that bond takes its own sweet time to break, its own sweet energy it takes to break, and hence the reactions are slower, or you can say in many a times your alkanes do not react. Whereas when we'll talk about alkenes and alkynes, when it comes to do a reaction, it has an option of using the weaker bond to break instantly and do the reaction. No matter you talk about alkane or alkene, both have at least one or two pi bonds, and when they will have to react with something, they will break their pi bonds first to do the reaction, and sigma bond will remain intact. And that is why their reactivity is much better than alkanes. And that is why we say that alkanes or saturated hydrocarbons are less reactive, and this is the reason why they are called as paraffins also. Paraffins are the substances which do not react with anything, or they are very less reactive and they are inert in nature. Hence these are called as paraffins also. Okay, so this is the generic information about alkanes, though we have not spoken much about what all different compounds or what all different chains we can form an alkane, how the structure will look like. We will be talking about all of these, how will we name them, we'll be talking about this, but first we'll talk about how to represent an organic compound on paper efficiently, or how many different ways can be there in which an organic compound, or you can say a hydrocarbon, can be represented on paper. Okay, so we will be talking about few different ways of representation. You can choose any of them, it's clearly your choice, but if you'll get any compound in a specific representation, you should be able to identify and you should be able to understand what exactly this compound is. So we have four different type of formulas. One is structural formula, another is condensed formula, molecular formula, and bond line formula. Okay, so first let's talk about the structural formula very, very quickly. Structural formulas are the ones where all the bonds will be very clearly seen. You can see the bonds between carbon, and you can see the bonds between carbon and hydrogens also very, very clearly. So the most open structure or most visible structure where all the bonds can be seen nicely is called the structural formula. It's the most expanded form of a formula. For example, as I have already shown you, if I talk about, let's say, an alkane made up of three carbons, how will I draw it? I will draw carbon, single bond, carbon, single bond, carbon, and the valencies. So this carbon has made one bond, so remaining three valencies. This carbon already has made the two bonds. This carbon has already made two bonds, so remain with the two valencies. This carbon has made only one bond, so there are three valencies. So this is how your structure will be, and then these valencies will be fulfilled by hydrogen. So here in this formula or in this representation of the molecule, I can see the bonds between carbon and carbon, and I can see the bonds between carbon and hydrogen also. And it is very clearly visible that carbons have made the single bond with each other, whereas carbon and hydrogen also have made the single bonds with each other. So you can just look at the structure, you can look at the formula, and you can know everything about that formula. Such kind of representation of a molecule is called structural formula. But what is the problem with this formula when it looks like so ideal structure where you can see everything? The problem lies when the chain grows, when the chain will have 20 such carbons or 25 such carbons, drawing all the carbons, then filling their valencies, showing the valencies with the hydrogen also, bonds with the hydrogen. So the structure becomes quite clumsier, and sometimes we lose the track of the carbon also. So only problem with this structure is it takes a lot of space, becomes clumsier if the chain grows, and that is why we have to find out a way which can simplify it a bit. Okay, so this is your structural formula. Structural formula. Okay, now what is the condensed formula? Condensed formula is one step lesser, or you can say one step easier representation of the formula, or you can say we can also call condensed formula as condensed structural formula, where we omit some bonds and some will let it remain as it is. That means, see here in the structural formula, we can see the bonds between carbon and carbon as well as the bonds between carbon and hydrogen. So what we do in condensed formula is we do not show the carbon hydrogen bonds, but we still show carbon and carbon bonds. Let me just explain you what do I mean. So I'm taking the same example here. I have carbon, carbon, carbon. I have shown the bonds between carbon, carbon over here. I have not shown the bonds between carbon and hydrogen over here. Why? Let me explain you. Let's assume this is carbon 1, carbon 2 and carbon 3. Carbon 1 has made only one bond. So that means it is left with three more valencies. So rather than showing those three bonds, I mentally calculate that there are three valencies which can be fulfilled by three hydrogens, and hence I will directly write H3. A little bit of mental calculation, but it will simplify it to a greater extent. Similarly, look at the carbon 2. It has already made two bonds. So basically only two valencies have left unfulfilled. If I'll take two hydrogens, both of these valencies will get fulfilled, and I can write it as CH2. Ignore this 2. This was to just number the carbon. Now come to carbon 3. Again, it has made only one single bond over here. So that means three valencies are yet to fulfill. And I'll place three hydrogens to fulfill these three valencies. And it will become CH3. So how can I write it? I can write it as CH3, single bond CH2, single bond CH3. So what all is visible? Carbon hydrogen bonds are not visible over here, but carbon carbon bonds are still visible. If you compare it with this looks a little more simplified and easy to write rather than writing the bonds, 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 bonds everywhere. Though it may not give you a very clear picture of the carbon hydrogen bonds, but all this is here in your mind, and this you have to write only when you are pro in writing the structural formula, and now you can calculate very fast. Initially, when you'll be writing compounds, I suggest you to use only structural formula because it gives you a very nice picture. It will make sure that you don't do any mistakes. Once you get pro in writing the structural formula, you can use condensed formula for representing your compounds. Next comes to the molecular formula, which is further concise form of these formulas. Molecular formula, what we do, we do not show any kind of bonding. We just count all the number of carbons, we count all the number of hydrogens, and if there is any other element present, count the total number of those elements. Just write it in one form. No bonding shown anywhere. So how many carbons are there in this formula? 3 carbons. So I will just write C3. How many hydrogens? 3, 2, 3. That means 8. So I will just write it C3H8. This kind of representation of a formula where I cannot see any kind of bond, only the total number of carbons, total number of hydrogens, that is known as molecular formula. It will not give you the clear picture of what kind of bonding exists in the compound just by looking at the formula. For that, you need to know a little more about it. You should know that it has the same form as this generic form. So generic form is CnH2n. So here n is 3. So basically it is following the general formula of an alkane. It is 3, 2 into 3 plus 2, hence this is an alkane. So here a little more smarter maths you need to do to figure out whether the particular compound given is an alkane, alkene or alkyne, though I have not spoken about alkene and alkyne yet, but the behavior remains the same. Next is bond line formula. Let me show you the bond line formula as well. So bond line formula is the most simplest formula because we are not doing anything over here. Neither we are writing carbon nor we are writing hydrogen. We are just showing the bonds, that's all, and everything else you have to assume. How? Let's see. So I have taken a line over here. This is my line. Okay, two endpoints of these line represents carbon. Okay, the line itself represents the type of bond. So if I have drawn just a single line, that means I'm talking about the single bond. Okay, endpoints represent carbon, and we are assuming that when one carbon is linked with the another carbon through the single bond, all the remaining valencies are already fulfilled by hydrogen, and we do not talk about it, or we do not write those valencies or represent it in the terms of hydrogen at all. So we do not do any kind of discussion about hydrogen, and we assume the valencies of carbon are fulfilled. We just show the bond between carbon and carbon through the single line, and the endpoints of each line represents that there are two carbons connected. Okay, how? Let me just show you. So if I have to talk about, let's say, the compound CH4. Okay, here I cannot draw a line over here because I am not making any bond with another carbon at all. There is no carbon, there is just one single carbon, but no carbon single bond carbon sort of thing over here. So if I have to do the bond line representation for this, I'll just draw a dot, and dot represents that this is a carbon and has made all the bonds, its valencies are fulfilled with the hydrogens already. So it's a very, very stupid representation in terms of the CH4. But yes, it makes sense when the chain grows. For example, if I talk about C2H6, C2H6, this is an alkane. By the way, you have to assume I'm taking alkanes all over here. I'm not taking any alkene or alkyne. When we'll talk about alkene and alkyne, I'll be discussing about those in detail. And right now, all the compounds which I'm taking are alkane automatically. So this C2H6 means two carbons are attached to each other. So this is one carbon, this is another carbon. Though you don't have to show the dot, I'm just showing you because you are learning it first time. And the line between these two dots represent, or you can say the line's endpoint represent that there is a single bond in between, and we are assuming that the carbon's valencies are already fulfilled. Okay, this is the representation of C2H6. Now this compound which we have spoken about, that is CH3, CH2, CH3, which has a general formula of C3H8. How to represent this in the bond line? So basically three carbons are there. Initially, when you are drawing the bond line, you may have to draw three dots, but later on you will get used to it and you won't have to draw the dots. Generally, the lines are in the zigzag manner. So there is one line here, another line here. Okay, the end point of this line is carbon 1, this is carbon 2, and this is carbon 3. All the three carbons are linked with each other through the single bond, and we are assuming that the valencies are fulfilled already. Okay, similarly, if I take C4H10, how will I draw it? This is carbon 1, this is carbon 2, This is carbon 3 and this is carbon 4. I'm assuming all the four carbons are linked through each other with the help of single bond. All the valencies, remaining valencies are being fulfilled by hydrogen, and we are not representing hydrogen anywhere. And in fact, we are not showing carbon also anywhere. We are just assuming that the lines and points are nothing else but the carbon. So this is called bond line formula. Easiest way of representation of the organic compounds, but you don't have this in grade 10, but it is good to have the knowledge of this because you may find it in NTSC and other competitive exams, and it makes easier for you to write it and simplify the way of writing, because when the chains are bigger, it is easy to draw this zigzag line rather than writing carbon 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 again and again. This is the best way of representation. In 11th and 12th, students choose to use this way of writing rather than writing the condensed formula or structural formula. Okay, so this is the basic information how a particular compound's formula can be represented in multiple ways. Now let's talk about the definitions, the exact scientific definitions of these terms. Though I have given you the major explanation over here, now we'll just go through the definition and we'll end the class here. In the next class, we'll talk about the nomenclature of organic compounds, because I have given you all the basic information required to know the naming of the compounds and how to list down alkanes, alkenes, and alkynes. Okay, so we have spoken about the structural formula already. Let's see what definition speaks about it. So structural formula identifies the location of chemical bonds. As I mentioned, you can see all the chemical bonds over there. Between the atoms of the molecule, structural formula consists of symbols of the atoms as carbon, 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 and hydrogens. So you can see all the bonds, you can see the hydrogens, so you can see the symbols of the elements being used, and the bonds between them very clearly can be seen in the structural formula. You connect the atoms by the short lines that represent the chemical bonds. One, two, three lines standing for single, double, or triple bond. Exactly. So basically, I have drawn this single bond between carbon, carbon. So I have drawn this single line. If I have to draw the double bond, I will draw it like this. Double line, and then the valencies have to be fulfilled by hydrogen. So you can see different elements, symbols over here, plus lines which represent whether there is a single bond, double bond, or triple bond. So this is the definition of structural formula. Next comes to the condensed formula. What exactly is the condensed formula? It is a semi-structural formula. That means it is a little short form of the structural formula, where we which is very easier to use. Why? Because it still uses the line in between the bonded atoms, but it is an easier and shorter way to draw the line bond structural formula because it omits the carbon hydrogen bond. So what we do is, the only shortcut we have taken over here is that we are not showing the carbon hydrogen bonds, but the carbon carbon bonds are still intact. So how will I write it? Look at it. So I will draw it as C, 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 and we'll write the total number of hydrogens directly. So here we have 1, 2, 3 hydrogens. I will write CH3. Here I have 2 hydrogens. I will write CH2. Here I have again 3 hydrogens, and I'll directly write CH3. Similarly, if I take an example of this compound, it will be C double bond C. So that means the bond between hydrogens are not shown. So it will be CH2, CH2. So this is my condensed formula. Next, let's quickly talk about the molecular formula. Molecular formula is what? Molecular formula is the one which gives the total number of atoms of each element in the molecule of the substance. That means we will be just counting the total number of atoms of each element and writing it together. So no bonding at all. We are not showing any kind of bond over here. So in the previous slide, I had taken the example of CH3, CH2, CH2, if CH3, sorry. If I have to write this in the molecular format, I'll just count the total number of carbons. The total number of carbons are 3. Total number of hydrogens are 8. Similarly, I had taken another example, CH2 double bond CH2. If I have to write the molecular formula of it, total number of carbons are 2. Total number of hydrogens are 4. And that is the molecular formula of this compound. So no bonding, no representation of the bonds over here. Only total number of certain atoms, certain elements atoms will be counted and written together. Okay, next is bond line formula, and the last part of this class to explain you how the different compounds, or how the molecular formulas, or how the structures of organic compounds can be written in a 2D representation. So bond line formula, it is a notation. Bond line notation is a shorthand way of writing the organic structural formula. It is the most easiest way of writing the organic compound. It is the shorthand representation. In bond line notation, what all we do, we do not show carbon and hydrogen atoms. Only bond between the carbon atoms are shown, and the vertices and ends of the line represents the carbon atom. So basically, this is what your bond line structure is. So ends of your line represents the carbon atoms. Any unfilled valencies on the carbon are assumed to be filled by hydrogen atom. This is something which I have already explained you. We assume that the valencies are fulfilled by hydrogen already, and hence we do not show hydrogens, we do not show carbon. All other atoms other than carbon plus any hydrogen atoms attached to them are shown. So basically, if I have any other group, any other element present in the compound, that is shown, or you can say that is written in the bond line representation. I can give you one example, though we will be talking about this in detail later on as well. So let's say if I have a compound like this, CH3, CH2, CH2, OH. This is my compound assume. So this is not the simple alkane. It has a new thing present in it, that is OH. Oxygen as a different element, and with oxygen there is a hydrogen attached on the oxygen, not on the carbon. This hydrogen is attached on the oxygen. So if I have to draw the bond line representation of it, I cannot choose to I cannot choose to ignore this OH. I have to write this OH explicitly on my bond line structure. So how will I write it? This is the structure of 3 carbons chain, and on this third carbon there is an OH attached, so I will write OH separately. Okay, even if you do not understand this right now, you will understand it eventually, because we'll be doing a lot of bond line structures and it will make sense to you as we'll go ahead. Basically, what we are trying to say, if any other element is present apart from carbon and hydrogen, and the hydrogen is attached on that third type of element, then we have to represent that element as well as hydrogen both in the bond line representation. We cannot choose to ignore it. We have to mention it explicitly. So this is about bond line formula, and this is about in total how we can represent organic compounds in different ways. In next class, we'll be talking about alkanes, different type of alkanes, what are different compounds we have to talk about in alkanes. Then we'll talk about unsaturated hydrocarbons, alkenes and alkynes, how their molecular formula, structural formula, condensed formula and bond line formulas are written. And then again, the list of alkenes and alkynes we have to do in grade 10 syllabus. And most importantly, how to name these compounds.